Hello, everyone. I hope you guys are doing great. So, if you've been following our blogs, in the last couple of blogs, we talked about differential equations. And in this video, we're going to talk about Laplace and inverse Laplace. Not only is this an important topic in electrical engineering, but we can use its application to solve various complex differential equations as well. So, in this video, we are going to talk first about Laplace, and in the coming blogs and videos will talk about its application with respect to the differential equations. So let's start with it. As we talked about in the blog, so Laplace is usually represented by a symbol like L like symbol. This is what is called the Laplace of a function. So if we are writing that, we have to find Laplace of a function, and that function is usually represented with the variable of t. Then Laplace of ft is the Laplace of a particular function ft, which is denoted by another function fs. So this means that after taking the Laplace of a function which is with the variable t, after taking the Laplace, it converts into a function which is of a variable s, and this is all what the custom follows. So how to write the Laplace of a function? So the Laplace of a function is written as it's actually an integral transformation. So it's an integration within the limits of it's a definite integral. So it's an integration within the limits of 0 to infinity e raised to minus st ft dt, where ft is the function of which we have to take the Laplace, and e raised to minus st is a multiplication factor. So this is the let's call it the mathematical definition of the Laplace transformation of any particular function. Let's take a couple of examples, although I've already included a table of various usual functions, the Laplace of various usual functions which we use. But let's see how we got to it. So I'll take a couple of examples so that it will set a base and set a basic understanding about how to find the Laplace of some complex functions as well. So let's talk about the first one, the most basic. Let's say the function is 1. That's it. This is a function. So we are going to find the Laplace. So the Laplace transformation of 1 is going to be integration of 0 to infinity e raised to minus st, and we are going to replace ft by 1. So we have 1 dt. So it's as simple as integration within the limits of 0 to infinity e raised to minus st dt. And integration of e raised to minus st is e raised to minus st over minus s. So just a basic rule, this minus s is going to come down in the denominator, and we have the limits from 0 to infinity. All right, so let me draw a line over here and let's continue. Minus 1 over s as a constant is going to come out. So we are left with e raised to minus st within the limits of 0 to infinity. If we place the upper limit, we have e raised to minus infinity, and if we place the lower limit, that's e raised to minus 0. And we know that e raised to minus infinity is 0. So I'm going to write 0 over here, and e raised to minus 0 is nothing but e raised to 0, because minus 0 is nothing but 0, and e raised to 0 is 1. So minus 1 over s times minus 1 is going to be minus, and minus is plus. So we have 1 over s, which is exactly what is mentioned in the table as well. Let's talk about another example over here. So we have now the function as t. Initially we had 1, now we had t. Now we have t. So the Laplace transformation of t is going to be again the same basic mathematical definition: 0 to infinity e raised to minus st times t times dt. A little bit complicated because this is a multiplication of two functions and we got to integrate this. So definitely we got to use the integration by parts. So the first I'm going to write t, because that's going to be our first part as per the Eilert rule. So this is the first part, this is the second part. So the rule says that first term is as it is, and we integrate the second term. So the integration of e raised to minus st is e raised to minus st over minus s, and here we have to place the limits. minus integration of differentiation of first term, so the differentiation of t is 1, integration of the second term, so integration of e raised to minus st is e raised to minus st over minus s, and this should be again integrated within the limits of 0 to infinity. Minus 1 over s is a constant, and we are left with t times e raised to minus st within the limits of 0 to infinity. Minus 1 over s comes out, and minus and minus, minus and minus becomes plus. So we have plus 1 over s, uh, an integration of e raised to minus st within the limits of 0 to infinity. All right, let's make some space over here. Let's come down. So now we have over here, I'm gonna write the upper limit should be written with the limit, since this is coming to be as indeterminate form. So limit t is tending towards infinity of t times e raised to minus t, and if we place the lower limit, e raised to 0 is 1 and 0 is just 0, and 0 times 1 is 0, so the lower limit is just 0, plus 1 over s. Integration of e raised to minus st is e raised to minus st over minus s within the limits of 0 to infinity. Now we're gonna just place the, in fact, we cannot really place the limit, because if we try to rewrite this, this is t over e raised to st, and if we place the limit, that's coming as infinity over infinity, which is an indeterminate form. So we're going to use the L'Hospital's rule over here, and this minus 1 over s comes out, so we have negative 1 over s square, because this s and s gets multiplied. If we place the upper limit, we have e raised to minus infinity, minus we have e raised to 0 over here as well. Now if we place the limit, so we use the L'Hospital's rule, so the limit remains as it is. The differentiation of the numerator is just 1, and the differentiation of denominator is s times e raised to st. Minus 1 over s squared, this is 0, and this is minus 1. Now if we place the limit, there is no more indeterminate form, because s is a constant, it's going to come out, so this becomes s squared. And if you place the limit, e raised to infinity is infinity, and 1 over infinity is 0. Minus minus and minus will become plus, so we have plus 1 over s squared. So finally we are getting 1 over s squared as the Laplace transformation of t. So from here we are getting an analogy which is really which is quite beneficial for us to save time. Laplace transformation of 1 is 1 over s. Laplace transformation of t is 1 over s squared. Laplace transformation of t square is 2 over s cube. Laplace transformation of t cube is 3, not 3, it's 6. 6 over 6 over um, s raised to 4, and so on. So notice a pattern. This is 0 factorial over s. This is 1 factorial over s square. This is 2 factorial over s cube. This is 3 factorial over s raised to 4, and so on. So we don't really need to do these derivations again and again. It's always advised to learn this pattern and eventually write the direct Laplace transformation of that particular function. Let's take another example over here. Let's say the function with us is e raised to at. So the Laplace transformation of e raised to at, e raised to at is going to be integration within the limits of 0 to infinity, e raised to minus st times e raised to at dt. The base is same, so the powers are going to be, this is the rule of exponents, so this can be written as e raised to a minus s times t times dt within the limits of 0 to infinity, and this can further be written as integration within the limits of 0 to infinity, e raised to minus of s minus a times t dt. Now, if you notice carefully, if s minus a is positive, if s minus a is positive, why am I saying that if s minus a is positive? That's because if s minus a is positive, let's for the moment write its integration. So its integration is going to be e raised to minus s minus a over minus s minus a within the limits of 0 to infinity. So negative 1 over s minus a is going to come out, and we have e raised to, there is a t over here as well, and we have e raised to, we place the upper limit, or let's for the moment write it as e raised to minus 1 minus s minus a times t within the limits of 0 to infinity. Now if s minus a is positive, this expression will be negative. And if we place infinity, that will be negative infinity, and this will be e raised to minus infinity, which is 0. That's why we have to ensure that s minus a should be positive. Otherwise, the value of the limit which we are writing won't really hold. So keeping in mind that s minus a is positive, upper limit is going to be e raised to minus infinity, and the lower limit is e raised to 0, which is 1. So this is going to be negative 1 over s minus a, 0 minus 1, because e raised to minus infinity is 0, and that's going to be 1 over s minus a. So this is the Laplace transformation of e raised to at. Again, something which is recommended to learn. And let's say the last but not the least in the usual functions is the function having the cosine. I'm going to do for cosine, but the same procedure can be done for sine as well. So Laplace transformation of cos of kt is going to be, first off, I'm going to rewrite cos. So a little knowledge of complex numbers is helpful over here. If you recall that in the world of complex numbers, e raised cos kt can be written as e raised to I kt plus e raised to minus I kt over 2, where I is the square root of minus 1, which is iota. So I'm going to rewrite this integral in terms of the Laplace as in 0 to infinity e raised to minus st, and I'm going to replace cos with e raised to minus kt plus e raised to minus I kt over 2 dt. So this becomes a 1 over 2 is a constant comes out. If we open up the parentheses, we get e raised to here we have a t is taken as a common factor. We are left with ik minus s. In fact, what we can do is uh, we can take minus t as a common factor. So we are left with s minus ik plus e raised to minus t is again taken out. We are left with s plus ik, and this should be this complete expression should be integrated with respect to t. All right. So if we integrate this now, we just read that what is the integration of e raised to at. So keeping the same thing in mind, the integration is going to be 1 over over here s minus minus of s minus ik plus 1 over s minus of s plus ik. We have to be a little careful over here when we write the Laplace. So simplifying this a little bit, this becomes 1 over 1 over over here we have 1 second, I have made there's a typo over here. It's better if we can keep it just like this, because writing this much, actually we are trying to simplify it, but there's no need to simplify. So let me just clear this up, and we can right away write its integrations. So the Laplace of so over here 1 over 2 is taken out. We can write it as Laplace of even if we don't write this expression. So now the Laplace of cos kt using this expression is written as Laplace of 1 over 2 e raised to I kt plus e raised to minus I kt. So 1 over 2 is taken out, and we read a theorem in the blog that the Laplace transformation of ft plus gt is the Laplace transformation of ft plus the Laplace transformation of gt. So that's what we wrote. That's what we studied over there. So now we can use the direct formula, as in what is the Laplace of e raised to at. That's going to be just 1 over s minus ik plus 1 over s plus ik. We take a common factor over here. We have s minus ik times s plus ik. So this is going to be s plus ik plus s minus ik. So over here, these two are cancelled. And what are we left with is we have 1 over 2, 2s over a plus b times a minus b. That's an identity. So that's it's a square minus ik square. So this 2 and 2 will be cancelled. This 2 and 2 is cancelled, and what are we left with is s over s square plus k square, because I square is nothing but minus 1, so minus and minus will be plus. So this is the required Laplace transformation of cos kt. And likewise, using the same concept, we can find the Laplace transformation of sin kt as well. Let's try to find the Laplace transformation of some of the combination of expressions. So let's take the first example, as we have to find the Laplace transformation of 3 plus 5t minus t squared plus 2 times e raised to 3t. So I'm gonna segregate all the functions. So first I have to find the Laplace transformation of 3, then the Laplace transformation of 5t, then the Laplace transformation of t squared, and then the Laplace transformation of 2 times e raised to 3t. 3 is a constant, comes out, so we are left with Laplace transformation of 1. 5 is a constant, it comes out. T square remains as it is. 2 is a constant, comes out, so we have Laplace transformation of e raised to 3t. Now it's just the formula based. The Laplace transformation of 1 is 1 over s. Laplace transformation of t is 1 over s square. Laplace transformation of t square is 1 over, sorry, it's 2 over, or 2 factorial over, if we call it that way, and 2 factorial is nothing but 2. So 2 over s cube, and of e raised to 3t is 1 over s minus 3. So this is the final answer for the Laplace transformation of that function. Right. So let's take one last example on the Laplace, and then we'll move to inverse. So we have to find the Laplace transformation of 3 times e raised to 2t plus 2 times sine square 3t. So again, we are going to segregate the terms. So we have to find the Laplace transformation of 3 times e raised to 2t, and then the Laplace transformation of 2 times sine square 3t. So 3 is a constant, comes out, so we have the Laplace transformation of e raised to 2t, and then 2 is a constant, comes out, we have the Laplace transformation of sine square 3t. So we don't really have a formula for the sine squared 3t. So what if we can convert it into a trigonometric function which is without square? We can do that because we know that there is a formula for the double angle identity, that sine squared 2t is nothing but 1 minus cos 6t over 2. So this is the Laplace. This is how it can be rewritten, and this 2 and 2 is just cancelled because 2 is eventually going to come out. It's a constant. So this becomes 3 times Laplace transformation of e raised to 2t plus Laplace transformation of 1. I'm just segregating, minus Laplace transformation of cos 6t. So now we can find the Laplace. Laplace transformation e raised to 2t is 1 over s minus 2. Of 1 is 1 over s, and of cos 6t, like we discussed earlier, it's s over s square plus 6 square, which is just 36. So this is the final answer. All right, let's move on to the inverse Laplace. So, like we discussed in the blog, the inverse Laplace is nothing but the inverse operation of the Laplace. So, how do we write it, or how do we represent it? Inverse Laplace will give ft, and that is nothing but the inverse of the Laplace of a function, which is fs. The same table is going to follow, just we have to read it the other way around, right to left. So for example, we have to find the inverse Laplace of let's call it 1 over s cube. So we are going to say that we are going to recall that, okay, I know that the inverse Laplace of t square, sorry, the Laplace of t square nothing but 2 factorial over s cube. So if this means that 1 over 2 times Laplace of t square is 1 over s cube, which is exactly what we can use over here. So we can say that the inverse Laplace of 1 over s cube is nothing but 1 over 2 times t square, because 1 over 2 t square is something over here. So if we take the inverse both sides, this will be just cancelled and the inverse sign will come over here. Likewise, we have the inverse Laplace of 3 over s plus 2. So 3 is going to come out. We have the inverse Laplace of 1 over s plus 2. And s plus 2 can be written as the inverse Laplace of 1 over s minus of minus 2. And now we recall that the Laplace of e raised to at is 1 over s minus a. So this is exactly following the same criteria. The only difference is a is minus 2 over here. So the inverse Laplace is going to be 3 times e raised to, a is replaced by minus 2. So e raised to minus 2e. Likewise, let's take a couple of more examples. So we have over here as the Laplace transform, the inverse Laplace of 2 over s square plus 9. So if s square plus 9 like expression in the denominator, we get an idea about it should be either cos or sine. So 2 is a constant, comes out. So we have L inverse of Laplace inverse of s square plus 9. 9 can be written as 3 square. Right. So, and now we know that, now we recall rather that the Laplace transformation of sine of 3t is 3 over s square plus 3 square. So if we can have 3 over here, we can have the inverse Laplace. And that's not a big thing, because we can divide by 3 and multiply by 3, because dividing and multiplying by the same non-zero constant is definitely allowed in mathematics. So the inverse Laplace of 3 over s square plus 3 square is sine 3t over here. Let's take a little bit complicated, or not complicated, but a combination of a couple of functions. So that's the inverse Laplace of 3s plus 1 over s square plus 4. So we don't know the inverse Laplace, or in fact the Laplace of such a function, which is this right away, but we can surely segregate these terms and get an idea. So how to segregate? I'm going to rewrite this as inverse Laplace of 3s over s square plus 4, because the denominator is constant, plus 1 over s square plus 4 over here. And this can be rewritten as L inverse, the inverse Laplace of 3s over s square plus 4 plus the inverse Laplace of 1 over s square plus 4. So over here 3 is a constant, comes out. We have the inverse Laplace of s over s square plus 4 plus the inverse Laplace of, this is again, this looks like the sign. The only difference is there is no 2 over here, because there's a 2 square over here. So no problem, we divide by 2 and multiply by 2 to get 2 over here. And now this can be easily written, because this is the inverse Laplace is cos of 2t. Why 2t? Because this 4 is nothing but 2 square. And over here we have, this is sine 2t. Why sine 2t? Because we have 2 over here and 2 square over here. So this is the inverse Laplace of this particular function. Let's look at another particular pattern of the Laplace transformation, which wants us to use the partial fraction. So I talked about this in the blog. I just gave you an idea about how to find the inverse, but here's the complete solution. So L inverse of 1 over S times S minus 3. So first off, we forget about Laplace and let's concentrate over the expression 1 over S times S minus 3, and we'll try to have its inverse, its partial fraction. So it's written as A over S first, and then it is written as B over S minus 3. So this becomes 1 is equal to A times S minus 3 plus B times S. So if we write S as 3, we have 1 is equal to 3B, which means that the value of B is over 1 over 3. And if you write S as 0, replace S by 0, so 1 is equal to minus 3A, which means that the value of A is negative 1 over 3. So we have the value of A and B, and now it can the A and B can be written over here. A and B can be written over here. So if the A and B can be written over here, then we can easily find the Laplace, because now it becomes inverse Laplace of A over S, and A is negative 1 over 3 over S, plus B over, so B is 1 over 3 over S minus 3. So this becomes an inverse Laplace of negative 1 over 3 over S plus the inverse Laplace of 1 over 3 over S minus 3. So negative 1 over 3 comes out. We have the inverse Laplace of 1 over S. Then 1 over 3 again comes out. We have the inverse Laplace of 1 over S minus 3. And this is pretty much straightforward. Inverse Laplace of 1 over S is just 1. And the inverse Laplace of 1 over S minus 3 is e raised to 3t. So as a simplified expression, this is e raised to 3t minus 1 over 3. So this is the final inverse Laplace of the function. Let's take one last example in this particular chain. So we have the inverse Laplace of 2s plus 1 over s times s squared plus 9. So again, it looks like the partial fraction is going to be really helpful over here. So we are going to first do the partial fraction of 2s plus 1 over s times s squared plus 9, and let's rewrite this as a over s plus bs plus c over s squared plus 9. So this becomes 2s plus 1 is going to be equal to a times s squared plus 9 plus a times s squared plus 9 plus s times bs plus c. All right, so if you're going to replace s by 0, then 1 is equal to 9a. So a is nothing but 1 over 9. If you're going to replace s by negative 1, then we have, I think, negative 1 is equal to, this will become 1, so negative 1 squared is 1, 9 plus 1 is 10. So we have 10a, where a is already 1 over 9. A is already 1 over 9, so this becomes 10 over 9 plus, in fact, minus of minus b plus c. So in other words, that can be written as, let's see, if it is taken over to the left, we have negative 19 over 9 is equal to minus of minus b plus c, which can be written as b minus c if you open up the parentheses. Let's call it equation 1. And I'm going to now replace s by 1, so that this becomes 3 is equal to, again, 10 over 9 plus b plus c. So from here, 3 minus that becomes 27 minus 10, which is 17 over 9 is equal to b plus c. Let's call it equation 2. So I'm going to add both the equations, so to find the value of b and c. So equation 1 plus equation 2 is going to give me a negative this is going to be negative 2 over 9 is equal to 2b, which means that the value of b is negative 1 over 9. And if b is negative 1 over 9, so the value of c is 17 over 9 minus of b, so minus of minus 1 over 9. So this becomes 2, because 18 over 9 is just 2. So we got the value of b and c as well. So the integration is now, the Laplace more precisely is going to look like the Laplace inverse of 2s plus 1 over s times s squared plus 9 is going to be a over s, so 1 over 9 over s, plus bs plus c, so that's negative 1 over 9s plus 2 over s square plus 9. So that's something which we have to find. So again, we're going to segregate the terms even more, this expression in fact. So that's going to be inverse of 1 over inverse Laplace of 1 over 9 over s plus inverse Laplace of negative 1 over 9s over s square plus 9 plus the inverse Laplace of inverse Laplace of 2 over s square plus 9. So 1 over 9 is a constant, comes out. We have the inverse Laplace of 1 over s. Then negative 1 over 9 comes out. We have the inverse Laplace of s over 9 is written as 3 square. I think you know why. And 2 is a constant, comes out. We have inverse Laplace of 1 over s square plus 3 square. And I'm going to multiply and divide by 3. Again, I think you know why, because that will then convert into the inverse Laplace in the form of sine. So this becomes 1 over 9 times inverse Laplace of 1 over s is 1. Inverse Laplace of s over s square plus 3 square is cos 3t. And inverse Laplace of 3 over s square plus 3 square is sine 3t. This is the final answer for this inverse Laplace of that particular function. So I hope this video was helpful to you. I hope you got an idea about how to find in what is inverse, what is Laplace, what is inverse, how to find the Laplace, and eventually how to find inverse. Inverse Laplace is a little bit complicated when compared to Laplace, because that's definitely the inverse operation. So we have to look for ways to simplify. I mean, we have to first learn the table and then come from right to left. But I think with enough practice, that will come on tips. So that's it for this particular video. And if you have any particular doubts, please post it down in the comments section. Thank you so much.